Okay, the goal of this video is to try and learn about images being formed. We're going to start with the simplest one, or maybe the easiest one, I guess, the image formed by a spherical concave mirror. And so I've got a light source in here. This is a mirror, and I'm just going to rotate it. Whoa, try not to, I just turned the power off, that's fine. Got to put this back. So that's a mirror right there. Put this back, about right there. And then there's going to be an image that shows up here, but in order to get to see the demo, we have to do the calculations and the ray diagrams first. So let's go up here to the main board. Give me just a second. And let's learn some terms, then we'll do the math, and then we'll be off to the races here. Okay, so we want to talk and real and virtual. I can explain that more in class, but basically, I'll say it this way. A real image is one that forms somewhere where you could place a piece of paper. Now you might, and actually see an image, or you could imagine putting a piece of film there and it would expose the film. You might be thinking, how are we ever going to get not real images? Well, whenever you have multi-lens systems or a lens and a mirror, the classic one being your eye has a lens, so you can actually see a virtual image formed by a mirror because the lens in your eye will image that other image. But so for now, just think of real images as ones where you could put a piece of film and actually expose the film, or put a piece of paper and actually see the image. A virtual image is one that your eye could see, but you can't put a piece of film there. So more on that as we get to different types of mirrors and different placements. Okay, so in order to make the electrical outlets, I had to flip my picture compared to what we saw in the demonstration over there. And let's get rid of this so it's not distracting me. We're going to have an object, which is usually some bright light source with a pattern on it. So that's what our object is. So it used to be like a candle or something. And then this is going to be the mirror. All right. And you see these points C and capital C and capital F labeled. Capital C means the center of curvature. So this is a spherical mirror, right? And there's some radius of curvature. That's what capital R is in most books. And so the point where the center of the circle is labeled capital C. The radius associated with that circle is capital letter R. Similarly, the focal distance is lowercase f, whereas when you're drawing a picture, I will try to draw focal point as a capital F. So capital F is a point, lowercase f is going to turn out to be this distance right here. Well, let's go ahead and label that. So this distance right here is F. And it's going to be handy to give a name to this dotted line here. That is called the optic axis. All right? So notice all of our distances and all of our object, our mirror, this thing here is the mirror. Everything is centered on the optic axis. So this is F. This here would be capital R, the radius. Now, this thing, the object, that's our light source with the pattern on it. Whoops, wrong pen. This distance right here is D capital, or D subscript 0, D subscript O for object distance. This height is the height of the object. Now, hopefully, if this is where our mirror is located, we can move this object around and find the image. And when we do that, or you could move the mirror, or you could move a piece of paper, this distance would be D subscript I, the image distance. And this height that I'm going to have some trouble labeling here is the height of the image. And there are some terms that we use, front and back. meaning front side of the mirror and back side of the mirror. So for mirrors, the front side is the reflective side, the back side is not reflective. For lenses, it's a little bit different. So let's worry about lenses when we get there. There are some equations that we can use for spherical mirrors. Those are listed right here. The focal length, I guess I could call it that. Let's do it that way. I like that phrase better. The focal length is half the radius of curvature. The object distance, image distance, and focal length are related by this equation. I sometimes just call this the 1 over f equation, just so I don't have to say it always. The 1 over f equation. This capital letter M is magnification. Magnification basically is you take the height of the image over the height of the object, and if it's bigger than 1, it's enlarged. It's positive. It's magnified with greater than 1. If magnification is less than 1, it shrinks in size. If it's positive or negative, that depends on whether it's flipped upside down. So in this particular case, we see the object is about, I don't know. Let's see. I got a ruler here. The object is 10 centimeters tall. The image is -6 centimeters tall. So for this particular one, we'd have -6 centimeters over, what was it, 10 centimeters? Which is equal to -0.6. So notice magnification has no units. It's 60% of this size and inverted. So, all right. And it turns out the heights relate to the image distances, but one thing you really want to pay attention to is this minus sign right here. So when you're doing magnification, you can either do height of the image over height of the object or negative image distance over object distance. Now, some sign conventions, and all of this is written down on page 20 of volume 5. Okay. Typically, well, so we've seen that these numbers can be positive or negative, right? So under what circumstances? DO is positive if object on front side. So if the object, and I should be clear, this is only true for spherical mirrors. The sign conventions are different for lenses and refracting surfaces. So it gets really confusing. I just want you to know that these are the conventions for spherical mirrors. All right, that's true whether they're concave or convex. There's always a front side and a back side. The front side's always the shiny side of the mirror. The back is where you're not doing anything. Okay, so DO is positive if the object is on the front side. In this case, D image is positive on the front side. This changes for lenses. Okay. If it's concave, right? A concave mirror has a positive focal length and it can produce real images here. Does that all fit on there? Just barely. So if the image is on the same side of the optic axis as the object, it's upright. Now you might be saying, why don't you just say whenever it's above the optic axis, it's upright? You've got to be careful. Later on, there's going to be multiple lenses. And what can happen is the first lens could invert the image and the second lens or mirror might not invert the image. In which case, right, you could have an image that starts out below. And in fact, the demonstration that we have, my object starts below the optic axis and the image ends up above the optic axis. So this is probably, a more general way to say it than what's up top and what's down low. That said, if you have a single object above here, the heights above the axis are positive and the heights below the axis are negative. So yeah, anyways. All right, and then what did I want to say about magnification here? All right. M is greater than 0 if upright. And there was a second thing. M, if I take the absolute value, greater than 1 enlarged. So let me explain what I mean by that again. If the magnification is greater than 0, both of these heights have the same sign. Okay, that's a sign of an upright image. Now, if the magnification is, if the absolute value of that is greater than 1, it's enlarged. If it's less than 1, it's diminished, it shrinks. Okay, so now that's all of our terms. Let's go ahead and do the math for this demonstration, then we'll show the demonstration and see if it works. So we're going to draw the rays to try and learn where everything is, but let's start right here. I didn't label the units on here because it's going to get so busy, but here's my optic axis. I drew this with a ruler. Okay, here's my object. Is that 10 centimeters tall? Let me see if I drew that 10 centimeters tall. I screwed up a little bit. Okay. So now, according to the manufacturer of that mirror, the radius of curvature is 841 millimeters. So think, what's the focal length? 1, 2, 3, here we go. It's what, about 420 millimeters, 0.5, which is about 42 centimeters. Now, I'm going to run out of room if I leave that there, so I'm just going to put that over here. Okay, that was just from the focal length is half the radius of curvature. Now, notice in this case, I have my mirror over here. A cool trick when you're doing ray diagrams, the curvature of the mirror, it turns out introduces all kinds of complications, especially when you're drawing ray diagrams. So what I like to do is pretend the mirror is entirely located here. So I'm drawing a fake mirror. Obviously the mirror is not flat, we just said it's spherical. But what I want to do here is I'm going to draw some rays, and instead of having my input rays stop at the mirror, I'm going to stop them at this pretend imaginary mirror location. So it's assuming that the mirror is flat enough that on average it's just all right here. More on that later. There's a thing called spherical aberration. Read about it if you care. Let's get going here. So let's draw the focal point. So that should be about right here. And I'm going to label the focal point, capital F, focal length is lowercase f. So notice 42 centimeters. You might be saying, shouldn't that be right here? Well, remember, it's 42 centimeters from the mirror. So 10, 20, 30, 42, it's kind of close. It's not perfect. Now, we're going to draw some rays and see where we expect things to go. Ray 1, we're going to go in parallel to the optic axis and out through the focal point. Oh, and I'm going to try and use the same colors I wrote up there. Sorry. Geez, that's not very, it's hard for me to draw on the board. Okay, whatever. I'm going to call this ray 1. So it goes in, I'm going to put a little arrowhead on it, it goes in this way, and then it goes out through the focal point. And remember, instead of going to the mirror itself, I'm going to go to this dotted line. It reduces the spherical aberration in your drawing. Okay, so I've got the arrowhead showing me which way it goes. Now, one thing I could do just to get in the habit of this is you can also back extend the output ray, okay? So that's called a back extension. In case the image is virtual, those are useful. So I draw the input ray, then I draw the output ray, and I also back extend the output ray. Let's try ray 2. In through the focal point, out parallel to optic axis. All right. All the way to the dotted line. Then it's got to come out parallel. Trying to make it so you can see while I'm drawing here. That's not very parallel, but I did the best I could. So I'll put an arrowhead here. I'm going to call this ray 2, and then it comes out this way. And what can I do? Back extend the output. Now I can already tell these back extensions aren't going to meet. These two do meet up. I expect this is where the image is formed. Right? So here's where the light rays started together. They spread out and then they come back. So we're expecting an image right around in here. All right? Somewhere in there. And now the last ray, this is kind of a fun one. You really only need 2 rays to find the image, but I think you'll see why I like to do the third ray. Jeez, I keep dropping stuff. In through the center, out through the center. Kind of got lucky here. Now this isn't going to reach the mirror, but you can kind of get the idea. It would meet up. It would meet up right about down there. So it goes in this way and then back out that way, and I'll label this one as ray 3. All right. Now you could back extend it as well, way down there. Cool. So out of all this, it looks like we're expecting an image right about here. Okay, so there's my image. Whoops. Because we've been drawing this to scale, I can literally measure the image distance here. It looks like the image distance is about 70 centimeters. So it looks like we found, let's just make this red. The height of the image, maybe you can guess what it should be. If you know the object distance and the image distance, right, you could probably see we're going to get negative 70 over 100. It should be magnified by negative 0.7. So that means it should be negative 7, and it is. It's about, my picture has about negative 8. Not bad for drawing on the board. It's very difficult. So notice height image, and I'll just say RD for ray diagram, was about negative 8 centimeters. So it's in the right ballpark. So the image is a little bit blurry, hard to draw, so maybe it's more like 72 or 75. So I think what I'm going to do is round these and just say this one's about 75 and this one's about negative 7.5. I'm kind of splitting the difference here, all right? So we've got about 75 centimeters and about negative 7.5. Negative, not because it's below, but because it's opposite the direction of the object. Okay, the object was up and it's below. That's why it's negative. All right, and like I mentioned, the magnification is about negative 70 centimeters over 100 centimeters, and I think, what do we say, 75? Magnification is about negative 0.75. It's inverted and diminished. Inverted because negative, diminished because less than 1. All right, so that's one way to do it. Let's keep going. It's kind of a long video, but we're just killing this thing. Let's do the 1 over F math now. What was it? 1 over F should equal 1 over object distance plus 1 over image distance. I want you to take a second and solve this equation for image distance. Pause the video and try and do it yourself. I'm going to show the answer in 3, 2, 1. All right, so I'm going to say, I guess I could take all of these off so I can work faster. This marker stinks. So common denominator is the trick. There it is. So, and just to save room, I'm probably going to erase all these steps and move this up so I have room to do the math here. All right, but we're going to do this so much, you'll kind of have this on lock. By doing this algebraically, you definitely don't want to plug in the numbers when you're doing this one, because we do it so many times. If you do it algebraically on test day, you're just going to be fast. So just get in the habit of doing things algebraically, then do it. We can check the units real quick. Meters times meters over meters minus meters, that's meters squared over meters, check, it works. So, or you can do centimeters. So as long as you do everything in the same units, all meters or all centimeters, we're good to go. Okay, and like I said, I'm going to move that up. So from our 1 over F math, we get, and I'm getting lazy now, so I'm just going to do this. Oh, okay, let's finish strong here. DO, DO. Can you see that? Is that on the board? Oh my gosh, long video. Okay. Okay, so that's just doing that. Where'd my eraser go? There it is. All right, so we've got our, let's punch in the numbers that we know from the from what we set up. So we're going to assume DO was given, HO was given, and this focal length was given, or well, the radius of curvature, which gave us that. So when I plug this in, I'm going to leave off the units. We get 100 times 42 over 100 minus 42. I'm going to switch black markers. This one's driving me nuts. Where's my calculator? What did you get? 72? That matches up really well with this image, right? So I rounded it to 75. We knew it was somewhere between 72 and 75. Oh, I'm in the middle of the video. Oh, that's all right. Yeah. I'll be right with you. That was Angus. Sorry about that, everybody. Okay, so D image. And then where were we go? Okay, so this matches up. Notice these two match up. We'll check this with the experiment in a second. And so out of this, I hope that you could find the magnification yourself. The magnification is negative D image over DI, which will be, I believe, what? 72, 100. I notice here there's, okay, whatever. Let's just get through this video. Should be negative 0.72. So from the 1 over F math, we predict this. Notice the height of the object, we can, well, let me write this equation this way. Magnification is also equal to height of the image over height of the object. I think that's supposed to be in red. Which tells us height of the image should equal magnification times height of the object, which is 7.2 centimeters. All right, so now we have a way to actually check this with a simulation, or with a demonstration. Give me just a second, capping these markers so I don't forget. What are we gonna do? We're gonna run this demonstration, and we're looking for the following. The image should be formed approximately 72 centimeters from the mirror, or about 28 centimeters from the object. So this is D image, 72, and this is not. Okay, but doing the subtraction between those, this one should be, what did we say? 28 centimeters. This distance should be 72. All right, let's go take a look at it. And this was pretty painful to set up, so I hope you guys appreciate this. All right, let's zoom this in. Okay, I've got a meter stick there, and now let me turn the lights out. Took a long time trying to get this just right. Is it that one? I think it's this one. All right, and is this on? There we go. Okay, so just so you can see this, I don't want to mess this up too badly here, but let me just show you. So I just took a light, and I put it inside of there. And so this front surface here, where it's got an arrow and a number 1 and 2 on it, I'm going to line that up pretty close to the front here. And then I can adjust the light brightness to minimum. And I think, what was it, color temperature? Well, let's see if you can see that. So now, this is where we're trying to look for the image. And I'm going to try and see if you can see that on the screen really quick. You can start to see the image. And now what I'll do is I'm going to try to stay out of the way and slide this back and forth a little bit. And so you can see no image comes into sharp focus, no image. I'm trying to do the best I can right about there. And this is a little bit wonky because this is actually, the image is now slightly below the optic axis. The object, this is the object, this face, glowing face is the object, is slightly below the middle of the mirror. So it's below the optic axis, which means the image is now slightly above. So notice the object is lower than the image. And now at this point, I'm going to try to line up this meter stick here with the middle of the mirror. And I get about 74 centimeters is right here. I don't know if you can see my finger at all, but right there, that's 74 centimeters. So we see that this matches up fairly well with what we expect. Oh my goodness, I need to stop this video. That was brutal. Oh, wait, the magnification. Ah! This is a tricky one. Okay, and the image height. So what we usually do, man, I'm glad I remembered that and didn't have to redo this video. I'm going to stick a ruler up here. Now, it's kind of awkward. And I measure a height of the arrow as 7 and change. 7 centimeters. So it goes from 30 to 23. Right? I don't know if you can see that. That's the inch side, so I'm having trouble doing it there. Maybe you can see the numbers on the screen if you can't, but it's quite close to 7 centimeters. Yeah, so let's do it this way, just in case. It's about 7 centimeters tall. Oof, and it's inverted, so that looks right. Okay, now I can stop this video. My goodness, that was brutal.